In this video, we discuss the Theorem of Pappus. It's a pretty cool theorem. It allows us to find the volume of a solid of revolution using centroids. I had a couple of students earlier this semester who inferred the Theorem of Pappus just through their own physical intuition. I think it's pretty cool that they were able to do that. So here's the theorem. It says, let R be a region in the xy plane, and let L be a line that does not pass through R. So let's say this is your region. Here's y equals f of x. Here's y equals g of x. And we've got x equals a and x equals b here. So that's our region R. And we're revolving it around a line L that does not pass through the region. So maybe our line L is over here. So it could be given by x equals L. Now here's the rest. It says, if R is the distance between the centroid of the region and the line L, then the volume of the solid of revolution formed by rotating the region R, or revolving the region R about the line y equals L, is given by the following. Volume is just going to be 2 pi times the distance R so that is an average radius of this solid of revolution. So if this is our centroid, let's say it's there, this is the distance R, so it's going to have coordinates x bar, y bar, and we rotate that about this axis, so we're going to see maybe something that looks like this over here. I'm trying to do a good job drawing the reflection. It didn't quite work. There needed to be the same size gap on the other side. Oh, it's bad. Sorry, it's a really terrible picture. But this was my region. And I'm taking it and I'm reflecting it, so it's going to appear over here in the reflection, roughly, obviously. Well, this says this Theorem of Pappus says you just take the circumference of the circle that has this radius of R. And since you're taking this whole thing and you're revolving it around, you take that circumference and you multiply it by the area of the region, A. And that's the volume. So if you're closer to that axis, well then that circle is going to be smaller. So that distance that piece is going through as it travels around in a circle is going to be a smaller distance. So we get this circumference times A, where the circumference is the average radius of your solid of revolution, which comes from just taking that centroid, the distance between the centroid and that line that you're revolving around, and finding its radius. So it's as if all of your mass is concentrated at that point, and we revolve it around, and then we say, okay, I'm just taking this area and I'm going through this distance. Well, what's the volume? It's going to be that. Okay, so that's the Theorem of Pappus. Let's apply it to something. So let's say we are asked to find the volume of the solid of revolution formed by rotating or revolving, the circular region given by x squared plus y minus 2 squared equals 1. And we want to revolve that about the x-axis. Well, that's just a circle. That has very nice geometry. It's very easy to just look at the circle and know exactly what its centroid is. So let's draw it. I'm comparing that equation of the circle to x minus x naught squared plus y minus y naught squared equals r squared. The center is 0, 2. So when x equals 0, y equals 2. And the radius is 1. Because I'm just reading that 0 and that 2 off from here. Whatever I'm subtracting from the x, that's our x naught. Whatever I'm subtracting from the y, that's the y naught. If you see a minus 2, it's a plus 2. So that's our center. If r squared is 1, then r equals 1. So we're going to go plus and minus 1 unit in all directions. And we're revolving that about the x-axis. I think this is cool. What are you going to see? That's what the reflection looks like. Here's our original region. When I revolve that reflection this way, what I end up with, I'm going to try to draw it. It's a little bit hard to draw. It's kind of this donut shape. I did the best I can. But yeah, you're just going to see that over here, and it's been revolved all the way around, and so you'd see, like, all you would see is just like one edge of this donut shape. It's like an inner tube. Well, according to this, the volume of the solid of revolution is given by 2 pi times r, where r is the distance from the axis to the center of mass, or the centroid of your region, and then you just multiply by the area. Well, this is easy, guys. Area is just pi r squared for a circle, and that radius was 1. So we just get pi times 1 squared, so our area is pi. And the distance from our center of mass, which is the center of the circle, to the axis is just 2. So the volume of the solid of revolution, get this, it's so easy, guys. It's just 2 pi times 2 times pi, 4 pi squared, units cubed. That's it. That's the volume of that little donut shape that we just found. Oh, it's a nice theorem. It's a very nice theorem. Okay, so let's do another one. This one might require just a little bit more work. So let's say we want to use the theorem of Pappus to find the volume of the solid of revolution found by revolving the region bounded by y equals x, y equals 4, and x equals 0 about the y-axis. So y equals x looks like this. Y equals 4, that's just a horizontal line. X equals 0 is right here. and we're revolving it about the y-axis. So in that revolution, we're going to see that reflection over here. Well, according to our theorem, if we want the volume of this solid of revolution, which looks like a cone, I just need to find the centroid of this guy, find the distance between that axis and the centroid, and then just multiply 2 pi r times the area of that little triangle. Let's find the area of the triangle first. Well, if y equals 4 there and y equals x on that line, this must be x equals 4. So here's my triangle. It's 4 units tall by 4 units. So the area is 1/2 base times height. Base and height are both 4. 4 times 4 is 16. Half of 16 is 8. So we get 8 units squared for our area. Now we need the centroid of this. That's a little bit harder, but it's not too bad. In order to find the centroid, first I need the mass of the region, which is just equal to density times area. And we're going to assume that the density is 1, and the area we just found is 8. So we have that. Now we need the moment about the x-axis. You could draw the triangle or rectangles both ways. I'm going to draw them this way. The moment about the x-axis comes from taking the mass of this guy, and the mass is density times area. We're going to integrate from y equals 0 to y equals 4. So I need mass times distance to the x-axis, essentially. I'm abusing notation. Let me try again. For that one rectangle, it's the moment about the x-axis. For that ith rectangle, we get mass times distance. Density is 1, so it's going to be 1 times the area times the distance. Now don't plug in 8 here, because we're talking about not the area of the whole thing, but the area of that little rectangle. Well, in terms of y, that area is just going to be x on the right minus x on the left times delta y. X on the right is just y. X on the left is 0. So area is y times delta y. And the distance to the x-axis is that x, or is that y value. So it's just another y sub I. So that's the distance. That's nice. So the moment about the x-axis is just the integral from y equals 0 to 4 of y squared dy. So we get 1/3 y cubed, plug in 0 and 4 and subtract, you get 64 over 3. All right. Now for moment about the x-axis, or excuse me, moment about the y-axis, I need mass times the distance to the y-axis, and the mass is the density, which is 1, times the area times the distance to the y-axis. And we already calculated our area. This was our area. Length times delta y. So that's y times delta y for our area. And distance this time is the average x value between x right and x left. So that's a x equals y and x equals 0. So we add those together and divide by 2. And so we end up with 1/2 y sub I squared this time times delta y. Well, I think I know what that's going to be. It's just going to be half of the center of, or the moment about the x-axis, because it's the same formula, but just with a 1/2 there. So we're going to get 32 over 3 here. Okay. Almost done finding the centroid. This did take a little longer. At this point, I think I might rather use the disk method to find the volume of the solid of revolution. But the moment about the x-axis is 64 over, well, Oops, let's put the formulas in. Moment about the y-axis divided by mass. Moment about the x-axis divided by mass. Moment about the y-axis is 32 over 3, and we're dividing everything by 8. Moment about the x-axis is 64 over 3, and we're dividing everything by 8. So we end up with 4/3 and 8/3. So we take this 4 and we're dividing it by 3. Let me draw my triangle again. X equals 4 divided by 3, so I'm dividing this into thirds, so it's 1 1/3, and y equals 8 divided by 3, so it's 2 2/3. So our center of mass is right there. And r is the distance from that center of mass to the axis that we're revolving around. Well, what's that distance? Isn't that just the x value? It's just 4/3. So according to our formula, volume is going to be 2 pi r, so that's the circumference of the circle that has this as its radius, just times the area of that triangle, because I'm taking that triangle and I'm moving it through an average radius of 4/3. So I get 2 pi times 4/3 times the area, which is 8. So I'm going to get 64 pi over 3 units cubed. That one was a little bit harder because we had to actually use our formulas to get the center of mass of this. But there is a shortcut for the center of mass of a triangle, which you're going to find when you do the associated homework problem. You're going to find the formula for the center of mass of a triangle in the homework. You could have used that here to more easily find that center of mass. And then once you found it, excuse me, you can find the distance from that centroid to that axis pretty easily. So that's it. That's the theorem of Pappus.